All right, we are back at AP Review. This is 2011 ABBC Free Response 2, and it's a table problem. So, before we do anything, before we even bother reading the context of this problem, you're going to be asked to do two things in all likelihood every single time. Number one, find the derivative of this as an estimate by using slope from this table. Number two, estimate the integral of this quantity by using some sort of area approximation method like an MRAM, an RRAM, an LRAM, or a trapezoidal sum. It's going to happen. So knowing that just kind of takes some of the pressure off. I haven't even read the words yet. I don't even know what they are, but I know those are two things that we're probably going to be asked to do. So let's see what we're actually asked to do. So a pot of tea cools. Cool. That's what it is in this particular problem. Don't worry. It's the same as all the other problems. A pot of tea cools. The temperature of the tea is modeled by the differentiable function h from time 0 to 10 inclusive, where time t is measured in minutes and temperature h of t is measured in degrees Celsius. The values of h of t at selected times t are in the table. You can see that here. Okay, part A. Use the data in the table to approximate the rate at which the temperature of the tea is changing, meaning approximate h prime of t. I think I totally said this was going to happen. At t equals 3.5. Show the computations that lead to your answer. So, in part A, they want us to approximate h prime of 3.5, right? The derivative of h. Well, derivative is slope if we oversimplify drastically. So the way they want me to do that is to use the 2 points that are around 3.5, which would have to be t equals 2 and t equals 5. So it's going to be approximately the slope between those 2 points. So h of 5 minus h of 2 over 5 minus 2, right? Which is going to be a 52 minus a 60 over a 3, right? So I end up getting that this is a negative 8 over 3, which you could leave it that way in degrees Celsius per minute if you want. Or if you want, since the calculator section, you can make this a negative 2.66 or 2.67 degrees Celsius per minute, right? They do not ask me to explain, but I do need to make sure that I have appropriate units, and I need to show my work that leads to my answer. Essentially, what they need me to show is that I understand that I'm using the old school slope, right? I'm using a difference quotient to find old school slope to approximate the derivative, and that's my answer. Part B. Using the correct units, explain the meaning of 1 over 10 times the integral from 0 to 10 of h of t dt in the context of this problem. And then, oh, shocker, here it comes, use a trapezoidal sum to approximate 1 over 10 times the integral from 0 to 10 of h of t dt. Cool. So again, walking into this problem, not knowing what it was about, I can tell you that just because it's a table problem, we're probably going to be asked to do the same couple things. So let's first start let's start with what this actually means. This is the average value formula, right? This is the formula for the average value of h of t on the window from 0 to 10, because it's 1 over 10 minus 0 times the integral from 0 to 10 of h of t. So this is the average value, or average temperature, right? So we can even just say average temperature of the tea, right? This is the average temperature of the tea over the time from t equals 0 to t equals 10 minutes, right? So, and I should mention, because anytime they have units, they want you to use it, so the average temperature in degrees Celsius. And if you had to, you'd squeeze it in the same way I did, and it's fine, right? And they do say explain in the context of this with correct units. So make sure that you say the time is in minutes, even though they've already said it. Make sure you say the temp is in degrees Celsius. And you need to mention that it's the average temperature. You do need to mention the time interval that's given, right? Now, could you say the first 10 minutes? Yes, because it's the time 0 to 10. Could you say over the 10 minutes because it's the only 10 minutes in this problem? Yes, that's fine, but you need to mention that time, right? Cool. Now we have to approximate it with a trapezoidal sum. So trapezoidal sums, sometimes you can use the shortcut where you essentially factor out 1/2 the height, but here the heights aren't all the same, right? The height from the 0 to 2 is a 2. The height from the 2 to 5 is a 3. The height from a 5 to a 9 is a 4, and then a 9 to a 10 is a 1. So the heights aren't consistent. The other big thing you have to be careful of is a lot of people accidentally forget the 1/10 in front, because the 1/10 isn't part of the trapezoidal approximation. The 1/10 is sitting in front of the thing that you're going to use the trapezoidal approximation for, right? So don't forget the 1/10, right? So now I'm going to do 1/2 the height times the sum of the bases, right? So the height is, if we draw like a little mini trapezoid here, right? the height is actually the difference between the x values, and the two bases are the y values on either side of that interval, right? So 1/2. Now, if you want to yank the 1/2 out in front of everybody, I guess you could, because the 1/2 is consistent. I'm going to leave it for now. 1/2, the height from 0 to 2 is a 2, and then the sum of the bases is going to be a 66 plus a 60. Now, it's a calculator section, so here's my suggestion. Write out the entire trapezoidal approximation to get your credit. After you write out your entire trapezoidal approximation to get the credit, type, and get an answer with your calculator, but you have to show that you understand how the trapezoidal approximation works. So that's the first trapezoid from 0 to 2, right? The next one's going to be 1/2 the height, which is a 3, right? From 2 to 5 is a 3, times the sum of the bases, which is a 60 plus a 52. And this is probably going to go into 2 lines for me because I didn't give myself enough space, and that's the way it works. The next trapezoid is going to go from 5 to 9, so plus 1/2, the height from 5 to 9 is a 4, and then the sum of the bases will be the 52 plus the 44, right? Plus, the last trapezoid is 1/2, the height from 9 to 10 is a 1, and then the sum of the bases will be a 44 plus a 43. If this is a non-calculator section, which is possible sometimes, I mean, this one is a calculator, but they've done it before, you need to make sure you convey this information at the very least so that if something goes wrong with your adding, you're not completely screwed. Because you have a calculator, you can type all this stuff in. You can clean it up as much as you want. It's up to you. When you've typed everything in, you're going to get that the approximate answer is 52.95. You can clean this up however much you want before you do stuff, right? Before you type it in, or you can just straight up say, screw it, I'm typing this entire thing in the order I see it, and I don't care. And again, that's degrees Celsius because that's the average temperature, right? Make sure you put appropriate units, right? Part C, evaluate the integral from 0 to 10 of h prime of t dt. Using correct units, explain the meaning of the expression in the context of this problem. So now we're not integrating h of t, we're integrating h prime. So this is going to use the first fundamental theorem of calculus. So in part C, when you integrate from 0 to 10 h prime of t dt, well, when you integrate a derivative, you just get the actual function. So I'm going to get h of 10 minus h of 0. Well, since this is the temp at t equals 10, and this is the temp at t equals 0, this represents the change in temperature from the start to the end of from the start to the end of the problem, essentially. So that's going to be h of 10, which was a 43 degrees, right? So it's 43 minus h of 0, which was 66, right? So I'm going to end up getting that this is a negative 23 degrees Celsius. So what this represents is that the T has cooled or dropped 23 degrees Celsius, right? So the T cools 23 degrees Celsius, or you could say, I think they say drops, right? Like temp drops. Cools 23 degrees Celsius during the 10 minutes, right? Because it's the difference from the starting temperature and the ending temperature, and that difference is a negative 23 because the T cools by 23 degrees, or the temperature drops by 23 degrees, or however you want to say it. But essentially, this is the net change in temperature over those 10 minutes. Finally, part D. At time t equals 0, biscuits with temperature 100 degrees were removed from the oven. The temperature of the biscuits at time t is modeled by a differentiable function b, and then they give us b prime. So it looks like I'm going to keep the table, but I don't think I'm especially going to need it. So they give us in part D, they give us a b prime of t equals negative 13.84 e to the negative 0.173 t. Now I'm going to put this in my calculator as y1, but I'm going to use x instead of t. So if I go to my y1, right, I get the negative 13, and I did a bad job of putting a decimal there, but oh my, still doing a bad job. Negative 13.84 e to the negative 0.173, and I used x instead of t because I'm in function mode. Okay, so using the given models at t equals 10, how much cooler are the biscuits than the T? So we know that b of 0 equals 100 degrees Celsius, right? So this is again the first fundamental theorem of calculus. If we integrate b prime of t dt from 0 to 10, we're going to get b of 10, which is the thing we want, right, minus b of 0, which we were given as 100. So essentially 100 plus this thing I'm going to make my calculator integrate is going to give me b of 10, and then I need to find the difference between b of 10 and h of 10, essentially. So I'm going to quit out of this. I'm going to go to 100 plus math 9, right? I want to integrate VARs, go over to my function y1, comma, with respect to x from 0 to 10. And I'm going to get that the temperature of the biscuits is 34.182 or 183. So I'm going to get 34.182 or 3 degrees Celsius for my biscuits, right? But I'm not actually going to use the rounded version of it. I'm going to use the, like, in fact, I shouldn't even round there. I should give myself a little bit more. 827.528, blah, 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 blah. And I'm going to go ahead and store that as B just for convenience sake. So I'm going to hit stow, and I'm going to do alpha B. Mostly just pick B here because it's already B in the problem, and that's B of 10, right? But they asked how much cooler are the biscuits. Well, the H of 10 minus B of 10 would be 43 minus the thing I just stored as B. And I'm going to get that this is an 8.817 degrees Celsius cooler, right? That's how much cooler the biscuits are. I subtracted the 43 minus the 34 point stuff, and I got 8.817 degrees cooler. The end.